So then how does a proof by induction work for one of these special kind of sets? Well, it's important to know that since we can uniquely label these countably infinite sets, that means we could write them in the following way. So here I've written my set out as a little lowercase s1, s2, s3. All I've done is, since I know that I can uniquely label them with 1, 2, and 3, I went and go ahead and put the first label first, the second label second, the third label third, etc. So you can do that for any countably infinite set just from its definition. So how does this help us with a new definition of induction? So if you have a statement where instead of using the natural numbers, you're using a set which is countably infinite, a proof by induction proceeds as follows. So we still have our base case. And so here for our base case, since we're not talking about the natural numbers, the very first one is not 1, but the very first one is the one that has the label 1. So for the base case, what we need to do is show that P of S1 is true right here. And then our induction step looks very similar to our original definition up there. We want to show that P of, well, since we're not talking about k's and k plus 1s, we're talking about elements of a set. Here we have to show that we can go from one element of the set, S, to the next element of the set. So if this, then that for arbitrary k. And then that allows us to conclude our statement. And again, this works in exactly the same way that our original way that we justified that induction over the natural numbers works. If we used our ladder example again, so here we have our infinite ladder that we're trying to climb. We remembered that our very first rung is like a 1, and then a 2, and then a 3, etc., etc. And this is a k, and that's k plus 1 up there. All we're doing is, if we have one of these countably infinite sets, then we're still climbing this ladder. The only difference is we're really just starting at a different place. So for example, remember when I talked about countably infinite sets, I said that one of a countably infinite set is five, 6, 7, etc., etc., etc. So that means that in our base case, we are not starting at 1, we are starting at 5. So I need to draw more rungs on my ladder. And so this set right here, that set really only occupies that part of the ladder. So that means that I really don't care about starting at 1. I need to start at 5. That's what this base case here says. Start at the very first element. So my base case is going to be 5. I start at that element. And then for my induction step, it says just keep going from there. I want to show that for arbitrary k, P of sk implies P of sk plus 1. So really, this might seem complicated because it's introducing new notation or a new definition, etc. But really, all that changes, if you change out this n right here, is really where you start on the ladder. Because we know that this set right here, since it's cannibally infinite, can be labeled with 1, 2, and 3, etc., like that. Then we know that it exists somewhere on this ladder right here. And so it just changes where we start and how we proceed along. We will take a look at a couple of examples of this.